Welcome everyone in this NPTEL online certification course on biological process design for wastewater treatment. So, in the previous lecture we studied regarding the coagulation, flocculation and sedimentation. So, we learned that there are essentially four sections or parts in which the sedimentation may occur, and those are the discrete sedimentation, then flocculent sedimentation, then we have the suspension or sedimentation, and then the fourth one which is the compression sedimentation. Now, in this the discrete particle theory actually helps us in finding out the terminal velocity that we calculated in the previous lecture. Now, today we will continue with the same and study the flocculent sedimentation also. In biological process design, generally up to flocculation settling it is good enough for studying. Some amount of suspension sedimentation may also happen where but it is good enough to understand the flocculent settling and it will be good enough for biological process design. So, we will continue further with respect to the sedimentation. Now, what should be an ideal sedimentation basin? We have studied the discrete particle theory and discrete settling up till now. What should be the ideal sedimentation basin? The ideal sedimentation basin should have a discrete particle settling. That means, the particles settling down are not affected by each other, and essentially in the sedimentation basin there are four zones. One is the inlet zone and certainly the outlet zone is at the last. Then after an inlet we have a settling zone, also a sludge zone in which the sludge is getting settled down, all particles are going, and then we have the outlet zone. So, we have four zones. Now, in the flow regimes like inlet and outlet, the distribution of flow should be uniform. So, the uniform horizontal velocity for the fluid which is entering the settling zone, and similarly we should have a even distribution of flow leaving the settling zone. So, these even distribution of flow is very important, otherwise disturbances may happen in the settling zone. Then we have uniform distribution of particles throughout the depth of the inlet zone up to the end of the settling zone. So, this is also very important for ideal sedimentation basin. The particles that enter the sludge zone are captured and remain in the sludge zone. So, they should not be going up and going in along with the outlet. So, once they are captured they should remain in the sludge zone itself. So, this is the ideal thing. Then particles that enter the outlet zone are removed from the water. So, if the particles are anyhow entering the outlet zone and they are not being captured, they should be removed from the water ideally. So, this is the sedimentation zones in a horizontal flow clarifier. So, we have the inlet. So, this is the inlet zone. Now, we have target baffle is there. So, that the flow which is coming out goes to the bottom, and then we have perforated baffles through which the flow is happening. So, now the flow has become uniform. Then we have a settling zone. Suppose the particle enters in this settling zone. So, this particle is certainly moving in this direction also and it is settling down also. So, it should settle down before actually it reaches the outlet zone. So, if it settles down here, so it will go into the sludge zone which is given here, and ultimately the particles which are not settled down and the flow will continue, and the outlet zone from here the effluent will go out of the system. So, this is for horizontal flow clarifier, four zones: inlet zone, settling zone, sludge zone and outlet zone. So, this is for horizontal flow clarifier. Now, similarly for upflow clarifier, the water is coming here and it is going here. So, the inlet zone is at the bottom because it is the water is going up. Then we have settling zone. So, in this case the water will go up, but the sludge will come down. So, this sludge will ultimately go into the sludge zone, and then the water will ultimately reach the outlet zone which is given here. So, we have inlet zone here, outlet zone, settling zone and the sludge zone for upflow clarifier, which is very commonly used in the industries for sedimentation. Now, settling in a upflow clarifier, suppose that we are now concentrating on any of these one sections. Okay. Now, here the particles are particle plus liquid with certain flow rate is going up. Now, under this condition the liquid is going up, but the sludge particles are settling down. So, this is there, and overall the top surface area is AS and this is there. Now, in the upflow clarifier the particle laden water enters from the bottom of the clarifier. At the bottom of the clarifier the velocity of rising water is greater than the settling velocity of particles. So, that means this VL is greater than Vs. So, it is trying to take up, or Vs or Vt, that means settling velocity of sludge or the terminal velocity of sludge particles. So, this is VL is always greater than this, and since the area as the water rises, the area through which it passes is increasing because of the cone shape of the clarifier. So, we can see here the area is continuously increasing because the flow rate is same and area has become greater, the velocity of liquid becomes lower and its ultimate maximum velocity is equal to the top surface area, which is AS. So, V0, the maximum velocity which the liquid can reach is V0. Now, we always want from the continuity principle the velocity of water decreases as it rises using this equation, where V is the velocity of water, Q is the flow rate of water, AC is the cross sectional area through which the water is flowing. Okay. Now, the velocity of particle remains the same, the settling velocity of particle can maximum be same. Given a large enough cross sectional area, the upward water velocity will become less than the downward velocity of the particle. So, ultimately because the area is increasing, the velocity of water will become less than the downward velocity of the particle. As a consequence, the particle will remain in the tank and then the clear water will leave, and because of this reason. In the design of upflow clarifier, the area of the top of the cone that achieves the separation velocity sets the top of is very important, and the placement of weirs for overflow of the clear water is also properly designed and it should be clearly be noted. The upflow water velocity that will enable the separation of the water from the particle is called overflow rate. So, this is V0 which was given here is called overflow rate, and this actually depends upon the maximum cross sectional area of the clarifier. Since it is the rate at which the water overflows the top of the tank into the weirs. Overflow rate is also called the hydraulic surface loading or the surface loading, because it has the unit of meter cube per day per meter square. So, like V0 is being given by Q upon AS, and Q is having unit of meter cube per day suppose, and this is having unit of meter square. So, this is meter cube per day per meter square. Theoretically, the efficiency of removal of discretely settling particles in a settling tank can be calculated based upon the settling velocity of particles, which we determined in the previous lecture, and the overflow rate which can be determined from this. So, this is how we calculate and design. Now, derivation of the overflow rate for a rectangular horizontal flow sedimentation basin. So, in order to remove a particle from water, suppose this is a sedimentation basin which is having a length L, height H, okay, this is, and the width is W, okay, this is width is W. Now, in order to remove the particle from the water, particle must have a settling velocity great enough so that it reaches the bottom of the tank during the time T0, the water remains in the tank, that is the detention time. So, that means suppose any particle which is entering here. So, it should reach the bottom of this settling zone before actually the water crosses this zone. So, this is very important. So, considering this, assuming suppose that T is the detention time for which a suspension is detained in the settling tank, that means T is the time under which the water will remain in the tank, and tank is having height h, length L and width W. Now, assuming the Vh is the horizontal velocity and Ut is the terminal settling velocity of the target particle. Now, we are assuming that Vh is the horizontal velocity and Ut is the terminal velocity. Now, the cross sectional area of the tank is h into W and the surface area of the tank is L into W. This is very clear. So, we have this tank which is like this. So, this is the L, okay, and this is the H and this is the W. So, from here we can clearly see the cross sectional area which is like this one. So, this is H, the height into W. So, that means H into W, this is correct, and the surface area of the tank which is this one. So, this is W into L. So, this is also correct. Now, going further, if suppose Q is the flow rate of the wastewater into the tank. So, we can represent the Q into cross sectional area into horizontal velocity. Okay. Now, this cross sectional AC can be written as H into W, which was here. So, H into W into Vh. Since the target particle should not resuspend during its flow along the length of the tank, therefore, detention time for the target particle like L is the length and Vh is the horizontal velocity. So, T is equal to L by Vh. So, this is the detention time. Also, the target particle should settle down before it reaches the outlet. So, that means the T should also be equal to H, the height divided by terminal velocity, which we determined in the previous lecture. Now, overall if we actually T is equal to L by Vh and T is equal to H by U2. So, we can write L by this horizontal velocity. So, we have two equations now which are there, and from this equation we can find out Ut is equal to H into Vh divided by L. Now, if we multiply both up and down by W for our case, so this W into H into Vh is actually Q and W into L is the surface area. So, this is the surface loading or overflow rate that we determined earlier. So, that means Ut and the U0 or the overflow rate, they should be equal for the ideal condition. So, if the settling velocity of particle is equal to or greater than the overflow rate, 100% of the particles will be captured in the horizontal settling basin. Unlike an upflow clarifier, some of the particles within Vs less than V0 will be removed also. So, this is particle. Now, for example, considering the particle having a settling velocity of 0.5 V0, that means the settling velocity is not greater than V0, but it is only 0.5 V0 and entering uniformly all throughout the settling zone. So, that means this is the all part. Here when we are saying that the settling velocity is V0, that means the diameter will be less than the targeted actual diameter, which have to be captured. Every particle greater than that diameter have to be captured. Now, it is not that only those particles will be captured, that particles less than that particular critical diameter will also be captured depending upon that where they are entering. So, suppose they have the terminal settling velocity of 0.5 V0. So, under that condition the particle which is entering here actually it will be captured, but those entering above that they will escape. So, that means that figure shows that the 50% of those particles, those below half the depth of the tank will be removed. Likewise, 1/4 of the particles having a settling velocity of 0.25 V0 will also be captured. So, all the particles above a certain size will 100% be captured, below that size also the particles will be captured depending upon that, depending upon the position at which they are entering. So, this is there. The expression gives the following important points. The terminal velocity should be greater than the surface loading of the tank, and this terminal velocity actually depends upon diameter. So, we have a particular diameter of particles which will be 100% be captured. Now, the surface area is more important than the height of the settling tank. This is very important. The surface loading is important parameter, that means the surface area is important than the height of the settling tank. That is why many of the settling tanks have very huge surface area. Higher the surface area, higher will be the removal efficiency and more will be the removal of final particles. All particles having settling velocity ut greater than the overflow rate will be completely be removed. Also, for particles which are having terminal velocity less than V0, Vt by V0 fraction will be removed. Still from less than that also the fraction will be removed. The percentage of particles P removed with a settling velocity of Vt in a horizontal flow basin tank designed with an overflow rate of V0 is Vt by V0 into 100%. So, this is the percentage of particles which can be removed from a horizontal basin. Now, this is another term which is very important in the sedimentation basin is scour velocity. The maximum horizontal velocity through the tank which does not allows resuspension or scouring of the settled particles. So, once they are settled down they should not be taken away. So, for that the horizontal velocity is given by this equation, and in this case F is the Darcy-Weisbach friction factor. It is unitless and its values vary in the range of 0.02 to 0.03. This K is the cohesion constant that depends upon the type of material being scoured, and it varies between 0.04 to 0.06. For sticky interlocking matter, the K value is taken to be 0.6, whereas for ungrounded sand material like it K value is taken to be 0.04. So, this is there. Now, actually this is 0.4, 0.6. Okay. Now, going further, there is another case that I told that in place of discrete settling we have flocculent settling. So, flocculate sedimentation is characterized by particles that flocculate during sedimentation. These type of particles occur, settling may occur in the case of like alum or iron coagulation, which is very common, in wastewater primary sedimentation and in settling tanks in the tincturing filtration. There is no adequate mathematical relationship that can be used to describe the flocculate sedimentation settling. The Stokes equation cannot be used because the flocculating particles are continuously changing in size and shape. In addition, as water is entrapped in the floc, the specific gravity also changes. So, this is there. So, and this is the flocculation settling. Now, there are different types of sedimentation tanks which may be used in the wastewater treatment. So, like first thing is that grit chamber for removal of sand and grits. So, this is used in the initial stages itself. So, we know that settling is happening here or sedimentation is happening. So, grit chamber is very common. Then we have a plain sedimentation tank for removal of settleable solids. So, this is used for settleable solid. Here we do not use any coagulant or flocculent because solids are by themselves bigger in size or they have very good density. So, they settle down. So, we have a plain sedimentation basin where the settling may happen. Then we have a chemical precipitation tank for removal of very fine suspended particles by adding coagulants etc. So, this is chemical precipitation tank for removal of very fine suspended particles etc. So, we can use them. Then septic tanks which are very common for doing sedimentation and sludge digestion together in the households. So, this is in the residences where there is no common effluent capture. So, for them the treatment has to be done within the residence. So, we have generally septic tanks. So, in these septic tanks sedimentation and sludge digestion occurs together. Then we have secondary settling tank which is very important for biological process design. So, after activated sludge or after trickling filter systems or in the simple ponds also this settling happens. So, secondary settling happens after activated sludge or trickling filter treatment system. So, this sedimentation basin or secondary settler is there and which actually uses sedimentation as one of the basic method. Then sedimentation basin design. So, for rectangular sedimentation basins at a minimum to provide the detention 2 tanks are used. Generally what we do is that for rectangular sedimentation basins we may use 2 tanks or more. These are placed together in parallel and maybe within a common wall also. This provides maximum flexibility in operation over a wide ranges of flow rates with allowance for one unit being out of service at the maximum flow rate. So, it is possible that one unit the sludge has been captured a lot and that sludge removal has to take place. So, under those conditions the one may be out, so another may be used. Many times in place of 2 tanks we can go for higher 4 number of tanks. However, as we go up the capital investment also happens. So, it may be possible that it may not be acceptable for the owner to have 4 tanks or otherwise, but 2 tanks are very common. Now, we will be solving some question here before ending the sedimentation thing. So, we have a problem. If a municipal wastewater plant is to be designed to treat a maximum flow rate of 60,000 meter cube of water per day, that in the settling basin or sedimentation basin it is desired to remove all particles of diameter 200 micron or 200 into 10 raised to minus 6 meter, and it is being given that for this condition the K value is 0.05, F value for is 0.025 and rho p is the particle density is 1.25 into 10 raised to 3 kg per meter cube. Now, we have to design a rectangular classifier having a ratio of length to width of greater than. So, the area which is available is in such a manner that we can use the length to width ratio of greater than 6. Overflow rate, in this case it is suggested that the overflow rate is at least 4 times the settling velocity. So, that means the V0 is at least greater than the 4 times of the terminal velocity and the horizontal velocity at most 1/3 of the scour velocity. So, that means the actual horizontal velocity actual VH actual is 1/3 of the scour velocity VH which was given in the scour velocity. So, this is what is being suggested. Under this condition we have to find out the dimension of the rectangular tank and determine the detention time also. So, this is being asked. So, actually in the actual condition any treatment unit or any plant manufacturer will only give this data 60,000 meter cube per day. So, we have to learn that from the particle size distribution we should know that what should be the target particle we should consider. Then from the literature we can find out these values or we can calculate. Then Roorkee also we have to determine the particle density. These assumptions are based upon our own condition. They may change depending upon the cost, the area available, etc., and the efficiency which is desired. Now, for the present condition we will solve at this the data given. Now, for this first we calculate the score velocity. So, it is score velocity is given by this formula. So, Vh is equal to 8 k by f under root rho p minus rho f g into dp. So, we keep all the here for density of fluid we are taking for the water. So, this is equal to 10 raised to 3 and we solve it using all the values which are given, and ultimately the score velocity comes out to be 0.08853 meter per second. Now, it is suggested that the actual horizontal velocity needs to be 1/3 of that. So, that means Vh by 1/3. So, it is 0.02951 meter per second. Now, next we calculate the terminal velocity. So, for this the terminal velocity equation is given by this. We are assuming that the laminar flow conditions are behaving, that is why directly the Stokes law equation has been used, and we are using the viscosity of water for finding out this. So, under this condition the terminal velocity comes out to be 5.44 into 10 raised to minus 3 meter per second. This is given. Now, under this condition if we use this terminal velocity the Reynolds number comes out to be this. So, which is actually okay. So, that means the our assumption of laminar flow condition is okay and we can go ahead. Now, it is suggested that the overflow rate has to be 4 times, this is 4 actually, 4 times the ut. So, this is 21.76 into 10 raised to minus 3 meter per second. This is the overflow rate. Now, if W is the width, L is the length and H is the height of the rectangular settling basin. So, W into H should be equal to flow rate divided by horizontal velocity. So, this is clear because Q, the flow rate is equal to cross sectional area into horizontal velocity. Now, this is the cross sectional area is actually W, the width into height, and this is the horizontal velocity. So, from this equation we can calculate that okay, W into H is equal to flow rate divided by the horizontal velocity which has been calculated already. So, from this the area, the cross sectional area, the height into width is coming out to be 23.54 meter square as per the present condition. Going further, similarly we can calculate the surface area using the length into width is equal to flow rate divided by overflow rate. So, the flow rate is given to be 60,000 meter cube per day. So, now it is converted into per second because the overflow units are in per second. So, we calculate 24 into 60 into 60, this is the unit will become in per second, and overflow rate is given to be 21.76 into 10 raised to minus 3. So, that means this area is coming out to be 31.90 meter square. Now, it is also given that L by W is tentatively equal to 6. So, under this condition, so here L by W was equal to this. So, L by W, and here from here we are taking L is equal to 31.905 divided by W, again divided by W is equal to 6. So, that means if you solve this the W value will be coming out to be 2.305 meter, the length will be coming out to be 6 into W. So, this will be 13.83 meter and the height will be obtained from the previous equation which was given here 23.54 L in W into H. So, this from here 10.21. So, we have all the dimensions are obtained to us. So, we will cross check with respect to the available area whether it is fitting to our conditions or not. Otherwise, we can modify this condition so as to further change these dimensions and still it should work out. The volume of tank is coming out to be 325.47 meter cube. The detention time will be, because this is the meter cube and this is the flow rate which was desired. So, if you solve it, it will be coming out to be 7.811 minute. So, this is the way we can design a settling tank for treatment of wastewater for a particular target of particle. So, this is how we go ahead. Certainly, we have to assume a lot of data and we can change this data depending upon the requirement and the space available, the cost of treatment, the efficiency desired, etc. So, this is how to design. So, we will go further ahead with the learning other methods related to biological process design in the next lecture. Thank you very much.